Thank you very much for showing up. So I'm going to talk about something that's, of course, not as impressive as deep, but it's maybe more relevant for you if you're running an InfiniBand cluster. So the idea here is that this is one of the not very often talked about topics in InfiniBand. It's actually routing. So we've seen a lot of micro benchmarks and a lot of actually data on performance that shows great performance and everything. But now the question is, I mean, what if we are running a very large cluster with InfiniBand? So how do we actually get fast, deadlock-free, so I'll talk about this in a minute, what that actually means, and routing for arbitrary InfiniBand networks. So we developed a mechanism that's actually available in OpenSM, so it's very relevant. And now we just want to tell everybody about it. So, well, that doesn't work. So the idea here is really that we have a lot of applications that use InfiniBand networks very intensively, and they use them in a collective fashion. So this is something that I don't need to repeat because DK talked about this a lot. So we have scientific computing, big data analysis, distributed graph algorithms, all the things we run, but they're all not using the InfiniBand network in a point-to-point fashion. Well, they all do point-to-point, however, they all do point-to-point together. So there are actually congestion effects in the network that we're looking at here. And the main influence in this congestion is actually the topology, which most of us probably can't change because it's some kind of engineering constraint, right? But the second thing we can actually change is the routing that we employ. So what does the InfiniBand spec tell us about routing? Well, the InfiniBand specs mandates deadlock-free, deterministic, and distributed routing, which is kind of, well, there's the sad smiley behind that, which is kind of an old thing. So today we would actually rather have adaptive routing. But, well, InfiniBand spec was written quite a while ago, so that's actually what we have to work with. And the OpenSM, it's the Open Subnet Manager. It's actually the standard tool that provides routing for InfiniBand. So if you ever set up an InfiniBand network, at some point you start this OpenSM, or this OpenSM is hidden in a switch, or something similar, so some kind of subnet manager, right? So I'm going to talk about OpenSM most of the time here. So OpenSM actually offers two optimal algorithms for two topologies. So OpenSM can optimally route perfect fat tree networks and perfect torus networks. Those are the two networks that are perfectly supported. So if you have one of those, then it's all fine. However, if you have a slightly different network, you're going to work with MinHop, most likely, which is the default algorithm when it falls back. When it tries to detect this or this, if it doesn't detect any of that, it falls back to MinHop. So this is the default algorithm, and of course there are commercial alternatives for subnet management software. So first thing is, one of the things that we often hear when we actually purchase InfiniBand networks, they always talk about full bisection and non-blocking and all this stuff. Well, problem being that yes, you can have a full bisection bandwidth network in hardware, and this is probably more expensive topology than a lower bisection bandwidth network. So this example is here just 144 port or endpoint fat tree, so this fat tree is non-blocking and whatever, full bisection bandwidth. But the problem is you will never see this in practice. So the reason why you don't see this in practice, the full bisection bandwidth, right, is a very theoretical reason that you can look up if you're interested in this. So Valiant wrote a great paper that shows that with static deterministic routing, you can actually not reach a full bisection bandwidth on this topology. So we could do it with random routing, but random routing is not supported by InfiniBand, as I said at the very beginning. So now we have to deal with this. So now we have to actually work within the InfiniBand limits, which is really deterministic, oblivious, destination-based, very simple routing. Right? It works more or less like in a large routing table in an Ethernet switch. So we have a linear forwarding table at each switch, which basically tells me the destination or the output port for every single packet, right? Not for a packet, but for every single destination. And then we have lit mask control, but that's not too relevant here. Okay, so this is just a small example to show you that it actually happens in practice. So what's the setting here? The setting is we have 8 port crossbars. Let's just assume this here because InfiniBand actually has 24 or 32 ports, but it's much too complicated to draw. So we have 8 port crossbars, and we have a full bisection bandwidth fat tree, which is also slightly drawn in a different way, and 16 nodes at the end. So the fun fact here is that each of those switches has 8 ports, so 4 go down, 4 go up, right? So it doesn't matter where you cut the network, you will always cut 16 links. So this is full bisection bandwidth, right, in theory. But the problem here is, even if you have that each of those links that goes up, so this one switch has 4 sources but 12 destinations, right? So he has 4 links going up, meaning that I can actually feed my data to all. I mean, if those 4 inject, in theory, each stream can have its own link. Right? But in practice, you have static routing, which means since we have 12 destinations, each of those links will have 3 destinations, because I have only 4 links. So, and if you have an unlucky communication pattern like this, process 1 is communicating with process 6, and process 4 is communicating with 14, right? They take the same link, even though they could actually take 2 links, but they don't because it's static routing, right? This is the limitation of our routing. So we will actually not see the full bandwidth. We will actually see it for a certain communication pattern, right? If we pick a lucky one, then we're fine, but if we pick an unlucky one, we're not fine. So the question is now, well, how bad is that really? Well, we did a couple of measurements on a slightly older system, so that's a single data rate, but just scale it down and FDR will behave exactly the same. So the funny thing is it starts at about 5 microseconds, as I said, slightly older system. The latency here, and as the congestion factor grows, it goes up, right? It goes up to 25, actually. So if you have congestion in the network, right, this is not endpoint congestion. Every process is communicating with exactly one other node. So this is just in-network congestion. So it can actually grow substantially. The thing is, you will never really observe this with ping-pong microbenchmarks because they're always, almost always an empty network, so you'll always see this. Right? We've seen lots of those benchmarks. The worst case is also really hard to observe, actually, because there you need to game a specific traffic pattern that actually generates a worst case. So we are more or less in the middle here. Same for the bandwidth. It starts really high and goes down. Actually, for this particular implementation, it went down to about gigabit Ethernet speed. Well, that's kind of a problem, right? So we did this so now the question is, where's reality here? So those are micro benchmarks at the very left. Those are worst case benchmarks at the very right. So we are somewhere in the middle, right? So we did a pretty big experiment on a 566 node cluster that has a full bisection bandwidth fat tree, right? It had a perfect fat tree. So we had no endpoint congestion. We picked random communication patterns, 1,000 different random communication patterns, and measured the overall bandwidth we got. So we got about 70% of the bandwidth. So this is actually good news because it's not less than 50. So it performs reasonably well. But for a full bisection bandwidth network, I would expect 100%, right? I mean, that's the idea of full bisection bandwidth. We just need to know this. This is a technical limitation. So now the question is, what can we actually do about this? How can we improve this further? I mean, is 70% really what we get, or can we actually go further? Well, that's an interesting question, so we investigated this. If you look at the subnet manager that I mentioned at the very beginning, which is actually doing your routing, right? This is the guy who assigns the routes to the links and the routes to the switches and everything. So this OpenSM offers multiple choices. So it offers you a min-hop algorithm, which really finds minimal paths, so paths of minimal length, right? It has up-down and down-up, which uses turn-based routing, which is just a restriction of paths of minimal length. We should keep in mind min-hop may actually create credit loops. So why do I care about credit loops? It's something that your network every now and then, like once a month or once a year, just gets stuck and needs to reboot. So this is something we don't want to do. So min-hop has this slight problem. It's very, very unlikely, but I'll talk about this in a minute. So we have this up, down, down, up, which cannot happen. So we have no credit loops in this network. We have F-tree, which is really only working on fat tree networks. So as soon as I add an additional link to like my storage or something, the fat tree network is not a fat tree, so F-tree is not going to work. But if it can, it's perfect. Then we have dimensional order routing and Torus to QoS, which is also great for Torus networks. And then we have LASH. So LASH is also something really nice. So now the question is, which one do you choose, right? If you start your OpenSM up, well, you have these choices. And of course, you have to look for your topology, right? If you have an F-tree, you start F-tree, fat tree. If you have a torus of some kind, you start DOR. And then you see, well, the question is if it's actually giving you a good routing. All of those will give you a correct routing, right? But is it actually good? Is it fast? Is it not fast? Well, you can run a couple of applications to just see, or you can run a couple of micro benchmarks. But that's really something you have to do to check if your network is actually configured correctly. So, well, but now the question is if it doesn't actually fit any of those topologies, like if you don't have a perfect fat tree, like this network, for example. So this is Tsubame at Tokyo Tech. So by the way, this is all a collaboration with Tokyo Tech going on at the Matsuoka lab, where Jens Domke is working. So this is the Tsubame machine, and here this is a perfect fat tree, but there's actually a kind of a departmental, couple of departmental workstations hanging off here, which destroy the perfect fat tree property. And most, if not all, of the real-world networks I've seen, they all have this, well, for most of them, it's kind of storage, right? They have this fat tree, looks great, full bisection bandwidth, all cool, but then, wait, I have disks, and so how do I plug the disks? Well, I plug them in a switch, plug another switch there, and so my fat tree is gone, and I can't run F3 anymore. So this is actually a more custom network topology, which is not a fat tree at all. This is actually 3 fat trees combined. But this is something you see in practice, right? If you have one of those topologies, what do you actually do? Well, we're going to talk about this now. So one question is first, how do you, in theory, you can always compute the bisection bandwidth of your cluster, right? So you take your, this is my InfiniBand cluster. The nodes are connected in this way, right? So bisection bandwidth is really defined to be the minimal number of cables I have to cut to bisect it into two equally sized partitions, right? I cut it into two partitions, and then I count the cables. If the minimal number of cables is actually as big as one of those partitions, we say it has full bisection bandwidth, right? This is what this definition of full bisection bandwidth. But the question is, again, this is what I mentioned at the very beginning, what do we see in practice? So in practice, we see less than full bisection bandwidth, right? Because we have this static routing, and that's a problem, but we have to work with it because it's a technological constraint. So we designed a benchmark that you can actually use that we call effective bisection bandwidth, which does nothing but try like 1,000 or 10,000, I mean, it's configurable, permutations sending nodes to each other. So it randomly permutes your network, randomly cuts your network in two, then it permutes, it peers up sending and receiving nodes, and then it actually does the communication, and then there are a lot of combinations here, and it gives you a number, and the number is the bandwidth you get out of your network. Right? But the cumulative bandwidth is not a single link bandwidth, what most people talk about. So you're really interested in the cumulative bandwidth. Okay, so then this is the only math slide, so I'm sorry. But the idea is really what you can actually do to solve this problem. So for those of you who are a little bit theoretically inclined and want to work on this, it's a very interesting problem, by the way. So you can model your network as a graph, that's fine. You can model your routes as a set of paths in this graph, it's also fine. So you have p times p minus 1 paths. If you have p endpoints, it's a very easy problem. So then you define the edge load, and that's something really crucial to this whole approach. You define the edge load for each of those edges in the graph. For each cable in the graph, you define the number of routes that are leading through this cable. And this is what you want to minimize. So the minimization problem here is actually you want to minimize the maximum edge loads over all edges in the graph, right? Because this is the upper bound to congestion, right? If each of my cables is carrying exactly one path, my maximum congestion is 0. If I have two paths, my maximum congestion is 1, right? So I want to minimize this, and this is very important. And so now the question is, how do we find an optimal routing that minimizes the number of the maximum congestion in the network? Well, it's NP hard, so that's kind of a problem, but that's fine. So we designed a nice algorithm for this. It's really, really, really simple, and we'll go through an example here. It's basically a local optimization. So we try to optimize this, and it really works like this. It starts at the default case, very similar to MinHop, then tries to find a minimum, but it'll get stuck in a local minimum, so I'm not claiming any optimality here. But it is much better in practice. And it strives for global balancing. So the example here is really simple. Let's assume we have three endpoints in a very stupid convoluted network with a lot of switches. So A, B, C, D, and E are switches. And we have only 3 endpoints. Nobody would build this, by the way. But it's for illustrative purposes here. So what we do is we start at node 0 and route to all the nodes with the minimum path search, right? So we try to find the minimum path from 2 to 0, which goes like this. And the minimum path from 1 to 0, which goes like this, and the blue and the green one. Then we annotate the edges with the path load. Then we do the same thing starting at node 1. So we do it like this, and like this. No, actually, this goes like this. And then we do it again starting at node 2. So same thing. So we find all the minimum paths, and after every minimum path search, we update the edge weights. So this is those small numbers with the arrows here are actually our edge foreboding index, right? So this is what we want to minimize. And this performs really well. So we get an edge foreboding index of 2 here. So, well, how does it perform in practice? And now we come to real values that may interest you much more from a practical perspective. So we looked at this is a 128 node cluster, InfiniBand again. And so we compare in this graph here, we compare the green one, and the green and the red one, which is very similar here, is actually MinHop and UpDown. So those are these default OpenSM algorithms that you would be using, right? And then we compare it to the algorithm as I just described, SSSP, and that's the effective bisection bandwidth. That's exactly what I told you at the beginning, right? You cut it into 2 equal pieces and do the communication, so you try to maximize your global bandwidth. And we get the simulation here gives you about a 5% improvement, but in practice, so this is the measurement, the simulation, this measurement, in the practice you get actually an 18% improvement due to some kind of buffering effects in the network, so the simulation is always optimistic in this case. So you can make your network 18% faster by switching the software you're running for routing, right? And so I'll be telling you how it works in a couple of minutes. The same thing for a larger cluster. So this is a DEIMOS cluster, was at TU Dresden. It's about 726 nodes. Same effect here. Simulation predicts 23% improvement. You can get 40 if you actually run the tests in practice. So there's also a lot of paper about that, so you can actually read about this. But now I just told you about how to get good routes for the network, right? So for the network experts among you, you will say, well, you know, that's really cool. We get 18%, 40% speed up, and actually on the Lomonosov system, which is a really large system, so 4,500 nodes, we measured an application speed up for Graph 500 between 10 and 20%. So, and that's coming for free, essentially. There's no new hardware or something. You just install a different software, right? Well, but the problem is, especially we've seen with this machine, is if you run it for a while, it'll just get stuck. Well, why? Because there may be credit loops. And so what's a credit loop? So credit loops is something that's also relatively interesting in theory. If you know a lot of details about InfiniBand, you know actually that it's a reliable transport protocol. So you will only send a message to the next switch if the next switch actually has buffer available. So that's credit-based flow control, right? So that means if you have a circle in your routing and a circular dependency on the next buffer, it may actually happen that all of the buffers are full and you can never actually send your switch to something to the next switch, right? And then your network is just stuck. It'll basically stop working, and all this, it will go back to the injection points. Your network stops, and that's what happened at the very beginning. At the early networks for InfiniBand, one way to work around this is just to have a packet timeout. So if a packet sits longer than 100 100 milliseconds in a switch, it just gets dropped. That's one way to resolve those conflicts, because they're very rare in practice. But it's not a very elegant way, and in fact, the InfiniBand spec does not allow this, but many people do it in practice. So how do we deal with those loops? Well, one way is you can prevent them. Right? You can use up-star, down-star routing, which really chooses an arbitrary route in the network, and then just goes only towards this route, and once it turned away from the route, it only goes away from the route. Right? That's up-star, down-star routing. Very, very simple. The only problem with this is it actually limits the routing options, so it may reduce your bandwidth. Right? So that's one issue. You can actually resolve them. This is now the nice idea. The nice idea comes from LASH, so from the group that was actually supposed to speak right now. Unfortunately, fell sick. So they developed this LASH algorithm, which is also in OpenSM. Very nice. The issue with this is it's actually implemented on top of DOR, so it won't give you the best bandwidth. And what we did, we combined both approaches. We combined the best possible bandwidth that I just told you how to get it, or a very good bandwidth, and the LASH approach. So we have now deadlock-free routing for this whole thing. The other option is, of course, to ignore it, but this is not really valid in the InfiniBand spec if you read it carefully. So, well, how can we avoid deadlocks? And this is now the LASH idea. So let's say we have this deadlock, right? Those are channels, and those are dependencies or routes here, and then we have this channel dependency graph. It's really easy. So this deadlocks, right? It has a circle. Very simple. Oops. So it's really easy, because what you can just do, well, we can just introduce a new channel. So we see we have a deadlock here. Well, what do? We introduce a new channel. So this is channel 2, this is channel 1. And we break the deadlock, because if we go on this transition, we just go into a new channel. So we can actually break every single circle in the network, routing circle, by adding a new virtual channel. So what is a virtual channel in InfiniBand? Well, it's called virtual lane. Right? It's something that's used for QoS usually. However, you can actually use it to make routes deadlock-free. Again, the nice idea by the Norwegians. And so we do the same thing. And we call this deadlock-free SSSP routing. So we break those cycles. The problem is, again, this is a second NP-hard problem. The first one is to find the optimal routes. The second one is to find the minimal number of actual virtual lanes you need, because a virtual lane is expensive. And in InfiniBand, you only have 15 virtual lanes. In practice, you actually only have 8. So if you want more, you need to go to Mellanox and convince them to give you more. But right now, you only got 8. Which is actually reasonable, because each of them costs you. Each of them needs separate buffers, so they actually have quite a substantial cost in the switch. So you don't want too many. So but the question is, does this work? Do we have enough virtual lanes? Because I told you every cycle I need to break with a virtual lane, right? And so if we do this in practice, well, it's not too bad. So we have a set of different topologies here. And this is the chick system that I told you at the very beginning, the 566, that actually only needs 3 virtual lanes. Right? This DEIMOS thing, the 40% improvement, needs only 2 virtual lanes. The worst one is the Europa system that was installed also at Jülich. That unfortunately needs 9 virtual lanes, so it wouldn't actually work with this routing algorithm. But you can work around this. But then you have Ranger system, much, much bigger, It's installed a tag with those very, very cool Magnum switches with 3,456 ports, and that will actually live with 4. So this is all workable in practice, right? And Tsubame only takes 2. So this mechanism actually works in practice, but now let's again evaluate the performance with a more practical setting. So many of you may be aware that all-to-all is kind of an important collective operation in MPI. So what we did is we compared all-to-all with MinHop. So if we just run all-to-all with varying message sizes on the full cluster, so on 128 nodes of this 726 node cluster, we get actually a 47% improvement for all-to-all performance compared to the other routing, right? Again, we switch a little bit of software, and we suddenly get much better performance. So we also did more experiments, of course. So there's, again, this effective bisection bandwidth benchmark, so we got a lot of speed up there too. And then NAS parallel benchmark, so this is something you're used to from DK Panda. So we also see about a 40% speed up for NAS parallel benchmarks if you scale them extremely. So if you really make them network bound, then you of course see the influence of the network, right? So that's the idea. So the other question then is, does it actually scale to large numbers of nodes, right? Well, kind of. The problem here is actually that none of the OpenSM does not really scale to large numbers of nodes. If you talk to people that work at very large installations, they always have trouble because it takes like 10 minutes to compute the routes. So you can see this, it's a runtime in seconds here. And one of the larger systems is Ranger system. If you just look at the MinHop time, right, that's 10 to the 2, that's a log scale. So this is actually like 5-6 minutes. And if you look at our approach, without deadlock resolution, it's much faster than MinHop. But DFSSSP, so SSSP is without deadlock resolution, DFSSSP is with deadlock resolution, is actually much, much slower. So it's like a factor of 2 to 3 slower because we need to break the deadlocks, find the cycles, and solve this approximate this NP-hard problem. So yes, it is slow, but it's only really slow if you have more than 5,000 endpoints in your network, right? So if you have your average size InfiniBand cluster, 2,000, 3,000, no problem, you can totally use this. It'll compute in less than 5 minutes. If you go to more than 5,000, you should be willing to wait 10 minutes for computing, depending on the speed of your CPU, actually. And then the performance improvement is also pretty substantial. If you look at Ranger, like Ranger routed with MinHop is about this performance. So effective bisection bandwidth is really low. And if you route it with different routings, then you will get a much higher performance. So it's the same for Tsubame and other systems. Okay, so how do you actually now get to use this stuff? Well, it's all nicely packaged in OFET, so it's released in OFET beginning from May 2012, so it's in the official OFET distribution. However, you should not use the first 2 versions, so don't use 14 and 15. The newest version includes a lot of patches, so that now actually works with if you have multiple rails in your InfiniBand network. So if you have multiple parallel networks plugged in, that didn't work with 14 and 15. So it's really easy. You can really just start OpenSM with the option -RDFSSSP or set this keyword in the configuration file, same thing. And then if you actually want to use the deadlock freedom with your MPI library, you need to configure a little bit more, and you need to run the OpenMPI or your MBAPIC or whatever MPI library with actually enabling different injection paths for the endpoints, right? This is extremely important, otherwise you'll not get deadlock-free routes. Okay, so as a conclusion now, well, what did I just tell you about? Well, we have a mechanism, so this DFSSSP mechanism gives you a better bisection bandwidth essentially for your network. It will not change any point-to-point benchmark under no load, right? So then expect magic. But if you have a lot of point-to-points going on at the same time in the network, you'll get a much higher bisection bandwidth, or even an all-to-all or some other collective operations. So you can get a huge increase in application performance as we've seen. So for Graph 500, it's probably the most extreme case that you can get like 20% speed up just by running this. And it's usable in arbitrary topologies. This is also one of the main things. So you don't have to have a special like fat tree or something network. It just runs at any InfiniBand topology, which I actually believe is one of the major strengths of InfiniBand. So you can really build whatever you want. You can cable up your system in whatever silly way you think, or whatever really your data center forces you to do, and it's still running, and this will also just run with this method. And it's really easy to use, right? So now I'm open for questions and comments. Thank you very much.